In the previous video I mentioned that the sort routine that we have here is inefficient. So let's look at why and a couple of things we can do about it. Well, the first one is, as you can see here, it's taken 81 iterations basically to make sure that those numbers are sorted. What we also learned was during each pass the biggest number is going to basically float to the bottom. So 10 is going to be bigger than all those, so it's going to make its way to the bottom. If we run it then for pass number 2, there's nothing other than the 10 going to be bigger than the 9, so the 9 would end up in the right place. Now, what we also should realise is that if we've got 10 numbers originally that's not sorted, we've got 9 comparisons to do. But now we've only got potentially 9 numbers not sorted, so that should only be 8 comparisons. Then 7 and 6, 5, 4, 3, 2, 1. So I definitely know that this inner loop here could be more efficient. It doesn't have to go around 9 times every time, right? That really should be like 9, 8, 7, 6, 5, so on. So I'll create another variable, right? Well, that will act as my loop terminator. So let's call it, I'll call it none loops. So it's in there, I'll just give the value, well actually I'll default it to the value 9. So instead of this here now going to 9, it will go to just less than num loops. So that part there will obviously be exactly the same as it currently is. Okay, 81. But what I want to do now, after I come out of this for loop, and before going back to the beginning of the other for loop, I'll say num loops minus minus. So just to take one off it. And if I run that now, the output will be exactly the same, but you can see that we've taken the number of comparisons down, right, from 81 to 45, and we're still guaranteed to have those numbers sorted. Now if that was, and that's only in 10 numbers, so if you had hundreds of numbers or thousands of numbers, you can see that how much of a difference that would make, and how much it would save in processing power. Now we're still not finished here. If you think about it, what else could go, or what else could we make efficient? In other words, well, let's say only one number was out of place, or 2 numbers were out of place. How many passes would it actually take then? So let's see. So let's pretend, right? Let's pretend that only one number, the 10, is out of place. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got those other numbers. The 10's in the wrong place, but the rest of them are in the right place. So with our code at the minute, right, it's still going to go around 9 times in the outer loop, but the inner loop is more efficient. So we're still taking up 45. So it's the outer loop now that we want to have a look at. And the best way to do this here is actually to look and see if there was ever a sort. So if something did need sorted, then it meant that it wasn't sorted beforehand. So we don't know how many times we want to go around here, so a while loop would be much more efficient than a for loop. And to help us do that, it would be a nice time to introduce a boolean type variable. So I'll create a boolean type called isSorted. And I'll give it the default value of false, because I'm not sure at this stage whether the numbers are sorted or not. So I'm going to assume that they're not until we know otherwise. So this for loop here will be changed to a while loop. And I'll just say while, the exclamation mark for not, so I'll say what while not is sorted. that's the same as saying while is sorted is equal to false. Alright, so I just keep open and closing brace, so that we have for the if statement. At the minute, this would be a continuous loop because I don't have any way for it to get back out again. So the first thing I'm going to do is say is sorted is equal to true. So I've decided to set it to false to make sure it goes under the while loop. First thing I do is set it to true to make sure it can come back out again. And then inside here, inside this inner for loop, where we're actually doing the test here, in other words, if a swap needs to occur, it meant that at that stage they weren't sorted, so we'll change is sorted equal to false again. So if I run that now, and you can see the sorting is still taking place, but we've now come from 45 down to 17. So our initial code, right, our initial code would have required 81 passes, even though there was only one number out of place, and we managed to get that down to 17. Now, in one other scenario, let's say the numbers were already sorted. Well, again, you don't know if they were sorted or not, so you're going to have to test that. So we're going to assume that we have to assume that they're not until we've tested it. So basically, we're going to have to do at least one pass. So the minimum we're going to get it down to is going to be 9. So you can see there now, as far as efficiency is concerned, we've taken that from 81 down to 9.